May. We're the Preventive Heatstroke cooling shelter by the Heatstroke design competition team. The team members are Andres Gomez, Eric Santana, and myself, Angel Velasquez. Heatstroke. Heatstroke is a serious illness that is closely related to hyperthermia, meaning that your body temperature is elevated drastically due to either being too much outside in the sun or you're doing a lot of exercise during that. And some of the symptoms that have been caused by heat strokes are dizziness, nausea, heat rash, and heat cramps. And some of the treatments that have been implemented for those people that have heat strokes are cooling them down, rehydrating them, or sometimes in severe cases you take them to the hospital. Here there's a chart that we have the average temperatures throughout the countries. More or less, Florida and Texas are the hottest temperatures throughout the nation, most closely because near the equator. And there's statistics that show there's like about 7,000 cases of heat strokes in the nation, which 700 of those are fatal and most likely have caused death in the nation. And some of them are caused in the schools, middle school, because of kids play too much sports and they just exercise a lot. So some of the preventative measurements that they have been implemented for people with heat strokes, we have the Heatstroke heat stress meter, which is a black bulb here, as you can tell. It measures the heat radiation being emitted from your body. And what it does is that it gives you an alarm whether a person is going to have a severe heat stroke or is going to get a heat stroke. One of the disadvantages about this item is that it's very expensive and not many people can afford it. And also the thing that we have is the cooling vest. The cooling vest is a portable device that you put under your torso, you press a button, and it starts cooling down your body. The bad thing about it is that it doesn't cover as much surface area as you want. So what our cooling device wants to do is cover the surface area as much as we can for the body. So for the project objectives that we have is build and test a portable and reusable cooling shelter. It should be able to work in two separate climates, such as a dry, hot climate and a humid, hot climate. It should be able to achieve our desired temperature in 10 minutes and hold that desired temperature for an hour, as for the competition standards. And also all the cooling has to be self-generated, meaning that no cooling from the outside sources should be inside. None of the cooling from any external sources should be just from the inside of our cooling shelter. So what we try to do is minimize cost by buying materials that are efficient. Also, we want to be able to have low power voltage. And also what we want to do is we're allowed to use water, and we want to be able to see if we can recycle that water in our system. But also we want to that's why we try to do is minimize the uses of water by recycling the water in our system.
Okay, for our initial design, we based it on the principles that hot air rises. This is why, as you can see at the top, there is a fan. We initially made this in hopes that it would basically create a vortex of air in order to get the greater surface area that he was mentioning before, as well as cool down the body of the patient at a faster rate. The downfall with this is, although the conical design is very good, at the very top, the area is much smaller. When that happens, it just restricts the airflow. So in this case, it was easily collapsible for us to make, but we still decided to move forward. In order to fix the problem that I was just discussing, we decided to make this square shape. The square shape would give us that easy surface area to get the hot air out as much as possible. We even installed fans to create a different type of vortex to go in this direction. The downfall is because of the 90-degree edges of this design, it was too turbulent, so we couldn't get the flow that we were looking for in the previous version. It was a very sturdy design, but it hurt us in the collapsibility department, which is one of the requirements by the competition. This is our final design. As you can see here, the diameter is 3 feet and the height is around 5.5 feet. We chose these dimensions because for the storage of the competition, it cannot be larger than a 3x3 box. So in order, we maximize the amount of space available while still being able to be efficient. This height design is 5.5 feet, and we made this design because there will be a 3-point buckle system at the top, This will be used to hang it from a tree, especially on construction sites. You can hook it up like even to a ceiling. Anything that is sturdy enough to hold it would work, because then what would you do is you would sit the person just basically in a chair, a harness chair, which will also maximize their surface area. It'll come over them, and what we'll have is these rings here you see is our mist system. It's just going to create a light amount of water, because if you can't drench somebody that is going through heat stroke, because they can suffer nerve damage. So this, we figured, was the safest way to use the water efficiently and safely at the same time.
Alright, now I'm going to be talking about our global design integration. Our shelter will require power as a source. So as you can see in this map, the whole world works in 110 volts and 220 volts, 50 and 60 hertz. Our machine will implement both sides, so we're on the good side. We also have 15 different types of plugs around the world, and our machine will also integrate to be able to use all around the world with all 15 different plug types. Our machine is also composed of various different components, such as the fan, the cooling system, the fan, the cooling system, our fabric, and our cooling peltier plates. All these parts could be individually changed by the end user. You don't have to buy a new machine, so it'll be easy for the end user to replace parts. Now we're going to move into engineering standards. We're going to be using 3 engineering standards: the ASHRAE Handbook, the ASHRAE 55, and the OSHA Heat Index Guide. The ASHRAE Handbook is like the Bible for the engineers when it comes to HVAC and creating air conditioning and heating systems. The ASHRAE 55 establishes the safety parameters when you want to build an environment where you're going to put a person inside. And for our OSHA Heat Index Guide, it just gives you basic information for workers when it comes to safety, when it's safe for them to work outside in high temperatures. The OSHA Heat Index Guide also provides tables and graphs that we're going to be using to estimate when a person could suffer a heat stroke based on different parameters, such as the temperature, the time of day, and the humidity. So in conclusion, we've come up with 3 alternate designs that he explained, and we already did our final proposed design. We also concluded that we're going to be using the fan, the cooling mechanism, and the cooling peltier plates are going to be implemented in our final design. For our future work, we're going to plan on doing a flow analysis on the cooling shelter to measure its efficiency. We're going to be doing, we're also going to be measuring the speed of the fan to see what's the most effective speed to create a good airflow. We're going to evaluate how effective our reflective shield is going to be around the cooling shelter. And we're going to also build it at the end, do a final build and testing to see if we're able to attain our certain temperature for 10 minutes and hold it for a whole hour. Thank you. This is our project, and now we're open to questions.
Do you have any medical physiological standards that you're using as a guideline to make sure that that patients, for loss of a better word, will be very well protected and this particular device will be very safe to use?
Well, we've done a study on the human body, and we have to turn the paper for the ASHRAE competition, and pretty much just a heat stroke is when your body reaches a temperature higher than
105 degrees.
105 degrees.
That's critical.
That's the critical point. That's when you start suffering a heat stroke. So we study the symptoms, and what we're calculating is that our project mainly is to lower the temperature. Once they reach 105, if you lower it lower than 105 for a whole hour, you're successful. Because if the body temperature of a human is lower than 105 degrees, they'll be safe and they won't suffer the heat stroke. So that's what we're basing ourselves on.
Well, what are the pros and cons for that kind of therapy? I mean, did you get that into consideration? What standards are you using to guide that?
Well, the thing about like nowadays, if a person's suffering a heat stroke, for example in a festival or something else, they're not liable of doing anything. They give you a bottle of water and let you cool down. but they don't touch you unless you're a severe case. When you become a severe case, they take you to the hospital. But if you're having the symptoms and other things, they just sit you there and they're not liable for you. So what we're thinking is, if they're not liable, you could put in a machine that you're still not touching them, they're not liable, and you can still lower the temperature more efficiently.
Oh, you're still
Than
liable.
by just giving them water.
If you're producing that, you're liable. If
Yeah.
you're saying this is gonna cool you off and they die, you're liable.
Yeah.
But,
That's where I'm going.
All right, I got you. Yeah, with the safety on the medicine side.
yeah.
And my question goes along with what he's talking about. My question has to do with the testing part of it. How are you going to test to see whether or not your portable shelter is going to work? It's going to have that design effect based on your objective. You say you're going to reach the desired temperature within 10 minutes and hold desired temperature for an hour. How do you know that's going to actually work?
What exactly the question is, are you
With
asking
the what?
if we're going to be able, how we're testing to hold the temperature, or how are we testing that holding the temperature lowers the person's body temperature?
For our final build, what we have studied is once we do a final machine and everything, we heat a kilogram of water. We heat a whole kilogram of water to more than 105 degrees. And then we put that inside the machine and we keep measuring temperatures.
That's not a good test because the body has heat generation involved. So, and a lot of it actually. And especially if you're at 105 already, generating a lot of heat. I'm assuming you're gonna have to be naked in there to cool off.
Depends.
So I mean, that would be ideal, depending on the person. But what I'm saying is, there's a lot, you got to think about a lot of what's happening here because that would be an emergency aspect, and your body heat generation is a lot to get removed. So you got to calculate how much heat generation you got from the actual body on that as well, which I don't see you guys thinking about that because just
Right now,
static.
Senior 1 is based on design alternatives. Senior
Oh,
2,
I-
we're going to start basing on testing and how to actually.
No, I understand this is an
testing.
engineering exercise. all
Yeah,
right?
yeah.
I know that everything here is an engineering exercise and it counts for something, but you have to understand the details as well. And just having a big drum of water in there that's not generating heat, you could probably duplicate it by putting a heater in there. You know what I'm
Yeah,
saying?
with 1 kilogram
So you
of water, we
could
put a heater,
use.
yeah.
What I'm saying is, calculate how much heat the body generates at a certain mass or person, right, at 105 degrees. You match that with a drum of water with the same heat generation with an electrical heater, and then you could actually calculate the heat drop in that.
Another way that we're gonna do is to calculate is that basically one of us is gonna be the guinea pig and we're gonna like
No,
no
That's not-
just like
not for
as-
105.
as a- no
no, that's not a
Well,
good
it's to
idea.
measure the how much heat is being emitted from like a regular body. What we wanted to do is not just machine it. but
No, we're not talking about putting him inside the machine.
No, but you understand that if you're at 98.6 degrees, your body maintains that no matter what,
Yeah.
all right?
Yeah.
So if you cool yourself, your body's gonna compensate by generating more heat. So you're in a pretty bad predicament here where what you really wanna do is, I mean, I'm thinking that what I said, which is a tank of water with a heater in it, matching your heat generation.
A 98
It'll be
degree, yeah.
it'll be a good test to do. But you know, when you're doing heat loss and all that, you got to take into account the temperature difference from the surrounding to the unit. You got a 105s. You're gonna you have to calculate all this. You could do that. You can't just blindly go and make something like that. I know there's an exercise. Is there a competition as well?
Yes.
So obviously there's a reason for that. But you need to calculate ahead of time before you do testing
Oh, yeah,
of
first.
your generation from your heat, and then how much heat you're gonna be removing by the CFMs of the air that you're removing from that with the same time as the water evaporation going through around from the mist. So you gotta have an idea before you even start testing it, if it's gonna work or not. And then test it, not with you, because you're at 98, and your body's gonna compensate, even if you go, it's not, you know, if you drop your body, it'll heat it up. So you gotta make sure you're at 105 and not you, but something at 105 with the same amount of heat generation, and then
So it could go down to 98
and see how if it goes
degrees,
down
yeah.
after a certain amount of time with the right CFMs that you calculated the water mist as well. I mean, it's a complex project, but
And it gets even more complicated with the human body,
Yeah.
Absolutely.
if you're gonna be liable.
oh, you're gonna be liable.
Somebody, you know, you have that at a park.
You're right at the school.
Why didn't you call the emergency services, you put them in there? I mean, I would not mention that. That's just an experiment you guys are doing, you know?
Yeah, this is
But
experimental.
I know lawyers and they're liable for everything.
I know. Yes?
I have a question or two questions on the design. You mentioned you're having a material fabric. Make sure that it's going to be able to sustain the weight of your fan. And my
Yeah, we're
second-
gonna build a structure and the thing is just for shade. Yeah, we're gonna have a base structure with the 3-point buckle system to the top. Everything is gonna adhere to that, like, circular
and so
structure.
my
for-
second question is, how does one get in? Are you doing a
It'll-
door?
The way it'll be is, we will have, you'll basically be seated and you'll be harnessed. And this design, because it's hanging, what it'll do is it'll literally be hung from the position and it will be
Pull
put
down.
over you.
How
Just
about,
lower it.
have you thought about maybe people that suffer from claustrophobia? How they would feel sitting in this contraption, pretty much?
I'll be honest, no, but that's the only reason we have our limitations with the competition, so that's why we made it as large as we could with the requirements we were given.
Well, a comment about that, that was for storage, is how you have it listed.
Yeah,
Yes,
so it's
Right. So that's not a design constraint to the size of your actual thing, it just has to be collapsible, storable into that space. So just for you guys. I similarly had a question about your design. One of the requirements that you'd put was self-generated cooling requirement, no external cooling. Are there any concerns that your power requirement violates that?
Well, according to the.
actually, we're allowed about 120 volts.
So you are allowed an external
Yeah, we have
electrical
external power
source?
outlet,
Yeah.
yeah. We
Okay.
have
They-
allowed water.
What they don't
allowed-
say is they don't want an outside cooling source. Like if you bring ice from a machine,
Right,
that's an
right.
external cooling source, yeah.
I was just making sure that form of a fan was allowable.
We also talk about, if you remember, a person having heat stroke may not be able to sit actually, may feel fainting or can lie down and stuff. And you were supposed to be saying something to that and I didn't hear that.
Yeah,
Yes, the person would be seated and we would have a harness.
What if the
Ooh.
guy just can't
You
sit,
can't do that.
sit
No.
down?
You can't do that because if you're fainted, you can't sit them down because the blood
Right.
will drop on the brain. You gotta have them flat down
Yeah.
or upside down.
They gotta be laying down.
Maybe lying
Yeah.
down, we talked about that specifically in the rehearsals. How would you do that? You said, yes, you'll think about it, but I didn't hear that.
I mean, this is why my first question is so valid. You cannot ignore the medical, physiological standards that are appropriate to this type of engineering project. You cannot ignore that. So you need to do some more lit review and some research on that and incorporate those components as appropriately and relevant.
And it may be as simple as turning this on its side, you know?
Right.
I mean, it could be
And
as
have a
simple as
fan,
that.
yeah.
Right, so.
Have it, you know, like he's saying, like a cylinder with a heater on top.
So we were thinking like if they're laying down, you have less surface area to cover.
That's true.
Absolutely, absolutely.
So the less surface area, that means we're gonna have to.
We'll put fans
Mhm.
either end and on top as well, but I'm saying you gotta keep in mind all that, what, the aspects of that, it's a very
Yeah,
complex.
yeah.
Unless, I mean, have you, is this the first year they have this competition?
Yeah.
Okay, that's a problem.
There'll be some
Yeah,
learning, there'll be some learning in that.
Right,
aspect
right,
as
right.
well.
You try to search
You can't
all
go
the
back and
papers,
see
there's
what
nothing. Yeah,
they were
this is the first,
expecting.
yeah.
So what, they gave you parameters, right? And all they gave you was just the storage, that's it?
Storage, capacity, the voltage allowed, water usage, and pretty much can be carried by two.
Oh, that's okay, I mean,
Yeah.
but keep all these options in mind, I mean, the body's very interesting problem.
Do you have anyone with some medical knowledge on your team or have access to someone with medical knowledge?
I do have some, yeah.
Do you use as a consultant or something?
Yeah, we're gonna be, during the summer, we're gonna be doing that.
One last comment, and I'm perceiving it from the questions from the team here. May I suggest when you start out, I didn't understand until I was questioning what you're doing. When you said shelter, I've got an 8x8 box, 8x room, it's a shelter. And then all of a sudden, someone drops the word competition. I'm thinking, competition? And then you've got the 10 minutes. I'm thinking the 10 minutes is that a competition parameter? Or is that a medical, I'm gonna save your life
Right.
parameter? So I was kind of, and then you say harness and hanging over the head. So, whoa. So up front, you might say, you know, our design parameters are based on the competition. And here's a little image of someone sitting in a chair with a thing over the top of their head. So we kind of need framing before you go down
Yes.
the tunnel.
That also, I have to say, that came up in the rehearsal, and I said that, just exactly that point. I said, we have to show people how this is gonna work. And you just say yes at the time, and still you're saying yes.
All right, thank you.
Okay?
All right, well, we'll see you next time.